Okay, so back to probability. This video is going to be more like specific problems with probability. So again, I wanted to go over what probability is. So probability, for specifically what we're talking about, probability in general is just like the chance that something will occur. Okay, so the equation or the way we're finding probability for this course right now is the number of desired outcomes over the total number of possible outcomes. So for example, if we're flipping a coin and trying to get ahead, like trying to get heads, the theoretical probability of that would be how many desired outcomes are there? Well, there's one head on a coin or whatever. What's the total possible number of outcomes? Well, I can have heads or tails. So the theoretical probability of a coin would be, our options are heads or tails. If we want to get heads, the number of desired outcomes, there's one head over what's the total possible number of outcomes, two possible outcomes. So that would be as a decimal 0.50, and then that would be as a percentage 50%. Okay, that's the theoretical probability of a coin toss. The experimental probability of a coin toss is not usually going to be 50%. If we were in class, I would give all of us, or give all of you, like 5 to 10 coins, and we lots of coin tosses here. I have some that I can do right here. So let's do a few experiments. So for experimental probability, so let's start off with 5 coins. So if I toss 5 coins, 1, 2, 3, 4, 5, and I'm gonna shake them up, I have 2 heads and 3 tails here. Okay, so let's do, we're trying to get heads here. Okay, so for 5 coins, I got 2 heads out of 5 coins, and that would be 4/10, which would be 40%. Okay, let's do 10 coins this time. So if I have 10 coins and I do a coin toss, let's see, I have 2 heads and 8 tails this time. So 2 heads, 8 tails. Oh, I'm sorry. It's not 8 here. It's 2 out of 10. Okay, I did it correct on this one. 2 heads out of 10 total coins that were tossed would be 0.2 as a decimal, which would be 20%. If I did 20 coins, I have to do 10 coins twice this time. So 20 coins, let's see. First time I get 1, 2, 3, 4, 5, 6 heads. Do it again to get 10 more. This time, this would be 7, 8, 9, 10, 11. 11 heads this time. So 11 out of 20, which would be, let me do the math here, which would be 0.55, which is 55%. This time, let's do 40 coins. So I need to toss these 10 coins 4 times. Here's first toss. 1, 2, 3, 4. So 4 heads. 5, 6, 7, 8 heads. 9, 10, 11, 12, 13. That's the third toss. This can be the fourth. 14, 15, 16, 17, 18. So 18 out of 40. And 18 out of 40 is 0.45, which is 45%. I'm gonna do 30 this time. No, I'm gonna go and do 50 and then you'll come see why I'm gonna do that. So 5 times. Okay, so 1, 2, 3, 4, 5 heads that time. So that's round 1. 1, 2, 3, 4. So that's 9 total heads. 10, 11, 12, 13. That's 3. I need to do 2 more. 14, 15, 16, 17, 18. That's 4. I need to do 1 more. It's funny that I got 18 exactly. Same as last time. And 19, 20, 21, 22, 23. So 23 out of 50. 23 out of 50 would be 96. I'm sorry. 46, sorry. 0.46, which would be 46%. Okay, so this time I'm gonna do 100 coins. I'm not gonna toss it 100 times, okay? What I'm gonna do is I'm gonna add 50 plus 40 plus 10, because 50 plus 40 plus 10 would be 100 total. So that would be 23 plus 18 plus 2, and that's 43 coins out of 100, which would be 0.43, which is 43%. Okay, so what I'm trying to show, and I feel like our data didn't really work well with this time, but sometimes it does better than others. What I'm trying to show you is what is called the law of large numbers. The law of large numbers says that as you increase the number of total possible outcomes in a situation. So in this case, as I increase the number of coins, my experimental probability gets closer to my theoretical, okay? So what that says is, I'm gonna write it down first. As I increase total possible outcomes, the theoretical probability will get closer to the experimental probability. Okay, and you can kind of see that here. So in this case, what is this? These are all experimental probabilities. Okay, the theoretical probability for this situation is 50%. Okay, so I started off with 5 coins, I had 40%. That's actually really close to 50%. But when I had 10 coins, I only got 2 heads, which was 20%. That's kind of far away from 50. 20 coins, that's a lot closer. 55 is a lot closer to 50. And again, it doesn't have to be over or under. We're talking about like the number that's getting closer and closer and closer to 50. So it could be like 51 or 49. Okay, it's like the same distance away from 50%. For 40 coins, this was the same percentage away because they were both 5% away. For 50 coins, I was closer. I got up to 46 that time. And then for 100 coins, it was only 43%. And I think part of the reason why is because I used this really bad percentage in there. But so other than this one and our initial one where I did pretty good, you can kind of see that the percentage gets better and better as I increase the number of coins. So like imagine what your percentage would be with 1,000 coins or with 1,000,000 coins. It would probably be a lot closer to 50% because here in this situation, when I had 10 coins, there was a lot of room for error, essentially, even though it's only an error. Okay, so that should kind of make sense. So the whole point of this law of large numbers is when you're reading statistics and you're reading studies or this percentage of, like, so many people were surveyed and this percentage said something, like, look how many people were surveyed. Like, was it 200 or was it 2 million? Because, like, the survey results are going to be skewed based on how many people were surveyed there, okay? So I hope that helps a little bit explaining that. Let's go over the types of probability problems that you will see on your homework in this class, but also that you would present or students will be presented with in their classes, but also like on standardized testing, probability is a really big deal. Okay, so some common tools for probability are what we just did, a coin toss. And again, we have heads or tails there. We could also use dice to do probability. And you can use six-sided dice or 10-sided dice or whatever. And just a heads up that standardized testing does not call it dice. It calls it a fair six-sided number cube. Or a cube. Or a fair nine-sided number cube or something like that. Okay. And if it's a six-sided number cube, our options are 1, 2, 3, 4, 5, or 6. Okay, we can also talk about a deck of cards. That's something that is very commonly talked about. So let's go over real fast a deck of cards, just because if you grew up playing like spades or different card games, solitaire, you understand or are familiar with the deck of cards. If you did not grow up playing card games, then you probably aren't familiar with it. And so let's just go over that. So cards, there are a total of 52 cards in a deck. We are not counting jokers here. There are 2 different colors. There are red cards and there are black cards. Okay, the red cards are hearts and diamonds. The black cards are, I shouldn't have drawn it because I can't draw a spade or a club very well. The black cards are the spades and the clubs. I was going to see if I could draw it. I'm not going to try. So this one's hearts or diamonds. Okay, so there's 2 different colors. So that means half of the cards are red, half the cards are black. That means that 26 are black and 26 are red. Okay, there are 4 suits, and we just wrote those suits. The suits are hearts, diamonds, both of those are red, spades, and clubs. Okay, within each suit, you have 13 different options. There are 13 different options within each suit. We have an ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, and king. Okay, so we're going to do some problems with deck of cards. Also, another one you see most commonly used in elementary school classrooms is a bag of marbles, and it'll tell you this many blue marbles, this many green marbles, this many pink marbles, or yellow, or whatever color they are. Okay, so let's do a few problems here. We've already done the coin toss. What's the probability of flipping a heads? The theoretical probability was 1/2 because there's 1 option or 1 outcome out of 2 total outcomes. Okay, we also have, let's do some dice problems. Okay, so what is the probability, so let's just say number 1, of rolling a 4? Okay, and this is on a fair 6-sided number cube. Well, how many 4s are on a normal dice or die? There's 1 number 4 on it. How many total numbers are there? Well, there's 6 total numbers, 1, 2, 3, 4, 5, 6. Okay, so 6 total numbers, so it's 1/6. All of our probabilities we're writing as a fraction, a decimal, and a percent. Okay, so 1/6 as a decimal, you would type in 1 divided by 6 on your calculator, and you get 0.16 repeating. You could also round that to 0.1667. And the percentage here, you move the decimal over 2 places, and you get 16.67%. So 3 answers, 1, 2, 3. Either one of those is sufficient. Okay, what is the probability of rolling a 3 or higher. Okay, so rolling a 3 or higher, that would be a 3, a 4, a 5, or a 6. How many possible outcomes do I have here? I have not total possible, like what's the ones that I would get correct here? 1, 2, 3, 4 options. Out of how many numbers are on a number cube? There are 6 total. So 4 out of 6 would be, that fraction reduces to 2/3. So there's the fraction. The decimal here is 0.6666 repeating. So if you wanted to round it off, you could. That's the decimal. The percentage is 66.67%, or we learned the other day that is 66 2/3%. I'm okay with either one of those. Okay, you could do lots of things here. You could, what's the probability of rolling a 3 or lower? What's the probability of rolling an even number, an odd number, a 5 or a 6, a 1 or a 6, things like that. Okay, so that's how you would do the dice problem. Let's do a few card problems. Okay, so what is the probability of drawing a king? Well, probability of drawing a king would be how many kings are in the deck. There are 4 kings, 1 for each suit. So 4 kings out of 52. You can reduce that to, they both divide by 4, so it reduces to 1/13. And then the decimal for that, 1 divided by 13 is 0.0769. And then when you make that into a percent, it's going to be 7.69%. So there's 3 ways to write your answer for that. Okay, you could ask what's the probability of, let's say, drawing a number card. Okay, so how many number cards are there? That's going to take a little bit of thinking to think about that. You can think about it in a lot of different ways. You can, I'm just going to go through and think, how many number cards do we have? Well, we have 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 number cards. Okay, how many 2s do we have? We have 4 2s, a diamond, a heart, a spade, a club. How many 3s? 4 3s. So it's going to be 9 times 4 is 36 total number cards. Okay. Again, you can think about that in a lot of different ways, or come up with that number a lot of different ways. I just counted up how many number cards we had and multiplied it by 4 because there's 4 of each. So 36 number cards total in the deck out of how many cards total? 52. Well, 36 divided by 52 is the decimal 0.6923. And then whenever I make that into a percentage, I get 69.23%. Okay, so pretty good odds of drawing a number card because there's a lot more number cards than there are face cards in the deck. Okay, so let's talk about independent events. So independent events are 2 events that don't affect each other, okay? So for example, when I flip this coin one time and get something, and then I flip it again, did my first flip affect my second flip? No, it didn't, because it didn't change what this coin's gonna come out of if I like am flipping it correctly or whatever. Or if I roll a dice and then I roll a dice again, if I got a 2 the first time, is that going to affect what I get the next time? No, because it's the same odds every single time you roll it. So those would be considered 2 independent events. Okay, so when you have 2 independent events and you're trying to find the probability of both of them happening, you multiply those 2 together. Okay, so when finding the probability of 2 independent events, you find the individual probabilities and multiply them. Do not add them, you have to multiply them. Okay, so for example, let's do the dice. That's a pretty easy one. What is the probability of rolling a 2, then rolling a 5? Okay, so those are two independent events. The first one is rolling a 2, so we have to find the probability of rolling a 2. How many 2s are on a die? There is 1 2 on a die. How many total numbers are on a die? Well, 1 6. So this is the probability of a 2. The probability of rolling a 5 is the same thing, because how many 5s are on a die? There's 1 5 on a die. Out of how many total options? 6 total options. When I multiply these together, that's how I find the probability of rolling a 2, then rolling a 5. So of both of them happening. So multiply fractions, 1 times 1 is 1, 6 times 6 is 36. So that is my fractional 1 out of 36. I can get a decimal for that, which is 0.0278. And then the percentage would be 2.78%. Okay. You could do the same thing. You'd say the probability of rolling an even number and then rolling an odd number. Okay, so the probability of rolling an even number, how many even numbers are on a die? Well, remember it's 1, 2, 3, 4, 5, 6. The even is 2, 4, 6. There are 3 even numbers out of a total of 6 outcomes. So this is even. How many odd numbers? I'm going to multiply this by, there's 1, 3, 5. So there are 3 odd numbers also out of 6. This is odd. When I multiply this together, I'm going to go ahead and reduce these fractions first. 3 6 is the same thing as 1/2. Times 1/2 is 1/4, and 1/4 is 0.25 as a fraction, which is 25%. Okay, the reason why we multiply these, and this should kind of make sense, the probability of rolling a 2 and then rolling a 5, that's going to be a really, really small probability, because it's rolling a very specific number of 2, and then after that you have to roll a 5. So think about all your options there. Of just rolling a 2, there's 5 other options, but then rolling a 2 and then rolling a 5, like it could be a 2 and then a 1 and then a 2 and a 2, so on and so forth. Okay, so it should make sense that it's a lot less probability to do this than it would be just for doing one thing initially. So that's why we multiply. If you added these two together, 1 6 plus 1 6 would be 2 6, which is like 1/3, which would be 33% chance. And that doesn't make sense that the probability goes up whenever you make it harder to do. Okay, same thing here. An even number than an odd number. This is a little bit higher percentage because there's more options here, but of rolling an even is 50%. So an even then an odd, that's 25%, because it's harder to get an even and then an odd next, because it might be even also. I hope that kind of makes sense. Okay, let's do a deck of card problem and then a couple of marble problems. Okay, so deck of cards for independent events. This would be number 3. What's the probability of drawing a 2? So probability of drawing a 2. Then a 3 if the card was put back. Okay, so this is still considered independent events, even like when you're not putting a card back, because it's not affecting necessarily what you're drawing the next time. It's just decreasing the number of outcomes. Okay, so I'm probably drawing a 2 for a deck of cards. How many 2s are in a deck of cards? There are 4 2s. Out of how many total cards? 52 cards. Okay, I'm going to put that 2 back and I'm going to draw again this time. So what's the probability of drawing a 3? So of drawing a 3, there are 4 3s. There are still 52 cards because I put that 2 back. If I didn't put the 2 back, there would only be 51 cards to draw from here. Okay, so to find the probability of this, I'm going to multiply these together. Again, we can reduce this. 4 out of 52 reduces to 1 over 13. 1 over 13, and when I multiply this, I get 1 over 169, which is a decimal. Let's see, 1 divided by 169, which is 0.005917. And when I move the decimal place over 2 times, that's 0.59%. So super low probability, like not even 1%. And it should make sense. Drawing a 2 and then a 3, that is very, very specific in a big old deck of cards. So that's not going to happen super often. It can happen, but not super often. Okay, so what about if let's do the same problem. So probability of drawing a 2, then a 3. Sorry, I'm writing really messy. Then a 3 if the card was not put back. Okay, so your initial draw of 2 is still the same. There's still 4 2s out of a total of 52 cards. So this is the 2. The 3 this time, there are still 4 3s, but how many total cards do we have now? We didn't put the 2, that first 2 that we drew, we didn't put that back in, so there are only 51 cards to choose from now. Okay. And the probability of this, 4 out of 52 reduces to 1 over 13. That does not reduce. This would be 4 out of 13 times 51 is 663. And 4 divided by that is 0.0060, which would be, move the decimal place over 2 times, 0.60%. Okay, so a little bit better odds than the one above it, but not much. Okay. Okay, last problem we're going to do is bag of marbles. This is the most commonly one you see on a standardized test. Okay, so you have a bag of marbles, and in your bag of marbles, we have 4 green marbles, we have 6 orange marbles, and we have 8 blue marbles. Okay, so with those, let's first find the probability of, so what's the probability of drawing 2 orange marbles if the first is returned after you draw it? Okay, so the probability of drawing your first orange is how many orange marbles are in there? Well, there is 6 orange marbles out of how many total marbles? 4 plus 6 plus 8 is 18. Okay, what's the probability of getting the second orange? Well, that first orange that you drew, you put back in there. So it's the exact same probability. It's still 6 out of 18. And we're going to multiply these together. Okay, let's reduce it first before we multiply. 6 over 18 reduces to 1/3 times 1/3 gives me a total of 1/9. And 1/9 is 0.1111 repeating as a decimal, which would be 11.11%. Okay, let's do that same problem. Let's do the probability of 2 oranges if the first is not replaced. So same idea, but I don't put it back in this time. Okay, so your first orange is the same as before. There are 6 total oranges out of 18 total marbles. The second orange, that first time you drew that orange and we didn't put it back in. So now there are only 5 oranges left out of how many total marbles? Well, now it's 17 total marbles. Okay, because I drew an orange, so there's only 5 left, 5 oranges left, and I took 1 marble out, so it's only 17 marbles. So when I do this, 1/3 times 5/17 would be 5 over 51. And that decimal is 5 divided by 51, 0.0980, and the probability would be 9.8%. Okay, so I hope that is helpful with probability. Your homework for probability should look very similar to this, these types of problems, and same thing on your test. Make sure on your homework you're doing the fraction, the decimal, and the percentages, or the percentage for all of your problems. And let me know if you have any questions.